close to the end of the course, and I feel that I need another extra class. I mean, it's the Christmas class was missing for me, and I'm still missing these 2 hours to finish what I want to tell you. So either I take the last Wednesday and allow Ravid to have actually a special exercise for you, as he usually does before the exam, just to go over questions. We always do this. So I'm not sure I will be in Israel to do it myself, but Ravid will certainly be able to do it sometimes in February. I don't know when you're ready to go over questions and so on. And maybe I probably take the last Wednesday as a class, just to finish things as I wanted. So just to remind you what we said last time very quickly. So we essentially talked about what we call the average code length, or sometimes we call it description length of data. So this is important. I mean, so this is a very fundamental concept. So we're talking about some random variable which has some probability distribution, which is assumed to be known. This is, of course, not the case in many realistic places, and X can be a very complex variable. It can be like pixels of an image, or spikes of many neurons, or voice, or whatever you have in mind. And the question is, what is the shortest possible description, or code length, or compression, whatever. There are many different names for the same thing, and which is essentially the expected over this P, the expectation over this P of the length of the descriptions of the objects of X. So X is, and this can be, as I said, a vector of things, or just, it depends how I view my data. So when I talk, for example, about text, I can talk about coding letters, I can talk about coding words, I can talk about coding sentences, I can talk about coding very long documents. So the object X is changing according to what I mean by description, and indeed the compression or the data description is going to be shorter the longer the object I'm thinking about. So for example, when I talk about compressing text in English, if I encode it on the letter level, it's very clear what it is. It's bounded by the entropy of letters, but letters are obviously not independent, so I can then talk about compressing words, and I'll have a shorter description, or I can talk about compressing sentences, and I have another short description. Essentially, what is the shortest possible description of something like English, which is essentially the entropy of English. So what we proved is that this is bounded by the entropy of the source, which was defined as the expectation with respect to this distribution of minus the log, or the log of 1 over the probability. And this turns out to be a very general relationship, which we usually call the Shannon's first coding theorem. It's a really an important result. And as I said, it's sometimes called lossless coding theorem. And we show that this bound, that the entropy is the shortest possible description, depends, of course, of what is the size of the variable that I'm measuring the entropy of. The entropy of letters is just this sum over the letters probabilities. The entropy of words is I need some estimation of the probability of words, which is a lot harder, because there are essentially infinitely many words, and I need somehow to estimate their probability. So to estimate the probability of words in English, you need a very large corpus. So to estimate the probability of sentences is of course much larger, and so on. This is exponentially. The number of objects is growing exponentially with the length. But there is something which is the minimal description length of English, which is the entropy per letter, which is the entropy of English, which is somewhere between 1 and 2 bits, actually, as far as we know today, for natural languages. Okay, yes.
Before that, the object, the shortest description?
The shortest description per length, per letter. So, of course, to describe words, I need more bits than to describe letters. But if I divide it by the length in terms of description per letter, it's going to be shorter, because I'm going to take advantage of the correlation between the letters. So, as I said, I mean, a perfect compression essentially is a removal of all the structure. This is one way of thinking about it. So, as long as there is some correlation in my data, so if my data doesn't look like entirely random sequence, in the case of bits and just like entirely random flips of coins or something like this, then if there is still structure there, some correlation which are not entirely random, then there is still a way of compressing. This is what we call there's still redundancy in the data. And if there's redundancy in the data, I can compress. That's the general lesson. So since words in English or in any language are not random sequences, they have structure, I can compress words better than I can compress letters. And since sentences in language are not random sequences of words, they have structure, I can compress sentences better than I can compress single words, and so on and so forth. So when we talk about a complex structure like language, the larger the objects I'm trying to compress, the better the compression is going to be. Okay? Now, and this is true in general. I mean, talk about, let's say, images. So I can compress a video better than I can compress single pictures, because there's a lot of correlation between consecutive frames of the video. They're very similar. So if I look at the compression length of a video, let's say in MPEG or something like this, some commercial compression scheme that we're all using all the time, it's actually taking a lot of advantage of the structure, the similarity of frames. So that's something I want to elaborate a little bit about this, because this is very, very important in practice and in all the applications of information that hopefully you're going to do in your own research, one way or another. It doesn't depend on whether you're doing theory or you're doing any applications, any experimental work or theoretical work in neuroscience today, one way or another is going to rely on this notion of compression. And I know that this sounds like a very, very general statement, but it's true. I mean, whether it's cognitive science, whether it's linguistics, whether it's neuroscience, whether it's vision or speech or whatever it is that you're studying, auditory, everything eventually boils down to this notion of information and description. Of course, I believe that the whole brain, I mean, the best model of the brain is built on such concepts. Otherwise, I wouldn't waste my time telling you about it. But it's also very important on practical terms. I mean, even if you're not thinking about the brain or just want to transfer information or doing information processing in any general sense, whether it's computational biology or whether it is engineering, machine learning, transmitting data, storing data, using data, whatever it is that is built on data, which is essentially everything in science today, including things like history and economy or whatever you have in mind. They all rely on data eventually, and data, the structure of data, understanding the intrinsic structure of data, is essentially equivalent to a good compression. So what I want to do in the first part of the first hour is just to complete this story in a slightly more general way. So we saw that this compression scheme is essentially assigning a code, which without loss of generality I can think as a prefix code or something like this, which means that I can always describe it by some sort of a tree. This is, as I said, I mean, it doesn't have to be a tree, but I can always find an equivalent code which is a tree. That's one thing I didn't quite prove. And actually, I can even find an equivalent code which is a binary tree. And as I said, I mean, the efficient coding is always corresponding to assigning my code words to the leaves of a tree like this. Okay? For example, a prefix-free tree. Now, I said that the code is optimal when a random walk on the tree generates the exact statistics of my source. So this is, in this case, the length of the letter is essentially the same, essentially equal to the ceiling of minus log the probability of the letter, where this sign ceiling is the lowest upper integer on this number log of p, minus log of p. So this minus log of p is not necessarily an integer number. It is an integer number. For example, if I take this to the base 2, and p's are powers of half, then it is an integer number. This is what we call a dyadic case. But in general, it will not be an integer number. So I can always find the two closest integers to such a number. So this is greater than some number, call it L1. So I can always bound my length. It's not exactly what I said last time, but it's very similar. By this and this minus 1. So I can always find an integer number between this and this number 1, plus 1, okay? Because it's in any unit interval, there's exactly one integer, okay? So if you take this number and you take it's this number plus 1, there's always an integer there. So what I mean by the ceiling is the lowest integer in this interval. It's either this. It's okay. So it can be just this number. Then I lose exactly 1 on average. But if this happens to be an integer, then it's just. If this is an integer, then I don't need to go this. So somewhere between these two things, I can find an integer number. Okay. And this, as I showed you, proves that I can get this bound to be very tight if I encode longer and longer sequences. So this was the idea of the last part of my proof last time.
Something that you said, that the random walk on the tree generates what?
Okay, so now I said something quite intriguing, that if this is the case, that essentially the length of the code is essentially very close to the log of the probability, because when I talk about very long trees, this difference, these numbers are going to be large, and this is going to be a very small number. So if I divide it by n, which is the length per symbol, this is going to be tight. That's what I said last time. I said actually the other way around. I thought about it later. It was a bit confusing maybe. I said that log p is between two integers, between L and L plus 1. Actually, this is the right way of saying it, but it's the same thing. So eventually, this 1 that I may have to add here, this is just above, a little bit above this lower integer, is going to be negligible when I talk about very long codes. Okay? So it's going to, per letter, it's going to be like 1 over n, and this 1 over n goes to 0 when n is large. Okay, so this is the nature of this asymptotic result. Now, so let's say that I'm actually on a perfect code, and then I know that this is an equality. Okay, up to this correction. So if this is an equality, it means that the probability is 2 to the minus, the same as saying the probability of x is 2 to the minus L of x. And this is saying, or again, in the same asymptotic sense that I meant before, right, like this. So this means that a random walk along the tree, which means I take a random choice, half-half. In the first branch, in the second branch, so in every branch, I just throw a coin. Okay? So what is my probability at ending a certain leaf? Just 2 to the minus the length of the leaf. Okay? So it's going to be a quarter here, and a quarter here, and a quarter here, whatever. This should be longer. Just make it consistent, and so on. So essentially, a random walk on a perfect code generates exactly the statistics of the source. That's what it means. Okay. So if I just take random numbers here and pass them through a perfect code, it would generate something which is statistically indistinguishable from my source. Now this sounds like crazy. So for example, if I have a perfect code of English, that says I have a tree that generates English exactly, it's a perfect compression. So this means that I now take random numbers, random bits, which I can generate with coin flips, or with, if you want to really perfectly random, you can take some physical process like, radioactive decay or something like this, and generate something which is the perfect randomness. I pass it through the code, And what I get at the end is statistically indistinguishable from English. Okay, so that's interesting. So a random generator will generate Shakespeare. You know, this was just like asking, what's the probability? It's a famous joke. It's a bit politically incorrect today, but what's the probability is a monkey typing randomly on a typewriter? This was an old joke. Will generate Shakespeare. I mean, this was actually one of the main attacks that were in the 50s against Shannon's approach to language. That essentially is telling us what is the probability that a random process like monkey typing randomly on a typewriter will generate something like Shakespeare. Okay, the probability is very low, but if this monkey has a perfect code of English, then essentially this tree will generate words and sentences in exactly the correct probability. So you see, there's something very powerful in this notion of a code. Essentially, a perfect code is a generator, what we call generative model of the source. So this is interesting. In some sense, if I could actually generate a perfect code of some source, I translated all the structure into random numbers, and random numbers will generate the structure. So a perfect code of let's say Van Gogh will generate pictures like Van Gogh. I mean, a perfect code of English will generate English. A perfect code of Chinese will generate Chinese, and so on. So it sounds okay. This is another way of saying that perfect codes are very hard to obtain. Okay.
Are there examples where they are saying like real world examples?
Yes, of course there are. I mean,
that really work that you believe in.
Yeah. Well, okay. So now let's go back to our main high-level topic, learning. Or statistical modeling, as we usually call it. So a good statistical model, let's say I want to model speech, I want to model language, I want to model images, I want to model neural data, whatever it is that I want to model. A perfect model is something which, if I initiate it randomly, which means just like walking randomly on this tree, will initiate something which statistically looks like my source. So a perfect model of Van Gogh will generate Van Gogh pictures. A perfect model of speech will generate speech, and so on. Now, so this is just, and this sounds, of course, in some sense implausible, but remember, this tree in this case will have to be huge. I have to encode not only sentences, but I have to encode whole books. And only then it makes sense that using this very large data set, I mean, a lot of examples of books, or I can generate codes which can come close to good models. But that's precisely what we do today in machine learning. And we actually generate codes. So what I'm trying to tell you that any statistical model is essentially a code. It's essentially an encoder of the data. Any statistical model. So I want to elaborate this idea a little bit because it's important. So I told you something about code. Okay, so code has this very funny picture. Essentially, without too much effort, I mean, in just one or two very simple theorems like the Kraft inequality and things like this, I got this result. And now I'm telling you, look, it tells us something very, very important about modeling. So statistical models, is something which is essentially attempting to do good description of the data, short description of the data. Because this is just the other side of the same coin. I mean, short description of the data means the model actually captures all the redundancies, all the structure. And I said that as long as there is structure, I can compress better. So a perfect compression really captures somehow all the structure of the data. So that's interesting. So let's try to take it a little further. So far when we talked about modeling, we thought about things like maximum likelihood, typically. I mean, there were sorts of variations, the maximum likelihood, maximum posteriori, maximum this, maximum whose. But essentially what we did is we took data and we took some parametric model, and then we looked for the parameters theta. So this is modeling. Let's maximize over theta the log likelihood of the data. Now this is the theta ML. So this was one prescription generic, one typical prescription, this is what people do most of the time. They look for a parameter which maximizes the log likelihood of the data. So I can think about it as minimizing the minus log data. It's the same thing. But this is just the length of the compression. So essentially, you can think about maximum likelihood as looking for a short code of the data. Because I'm trying to minimize the log of the likelihood, the minus log of the likelihood. So this is, in some sense, equivalent to the theta that gives me the minimal description length, as we usually call it. So MDL for this is minimum description length, which is, okay, so this is MDL. Now MDL looks like a philosophical principle. A good model is a model that is going to give me a short description. Now this sounds like, okay, an ad hoc assumption. But you see that it holds very nicely for everything that we are trying to say so far about data structure. So essentially this is just a manifestation of what I mean by a good description. A good model is a short code. Remember this. Now, yes, okay.
What makes it
so general.
Why is it short? What is the...
Oh no, because maximizing the likelihood is minimizing the minus log likelihood, which is the same as minimizing the description. That's it. Okay? And if I talk about very long data, the length of very long data on typical sequences is precisely the expectation of L. So it's the same thing. This is, again, this property of information, of entropy. What happens, by the way, if I don't have a good code? I have an approximately good code. So how much am I going to pay in excess of description if my code is not perfect? So this is very easy. Let's say that my code is actually, can be given, my length is actually not optimal, is this minus log Q. So which means that my source is P, but my code is not optimal code. It's actually a perfect code with respect to a different distribution. So we already saw in the proof that in this case my code length is going to be slightly longer. How much longer? Who said DKL? Yeah, okay. So so the access code length, so this, let's say this is LQ. So the average code length with respect to Q, with this code is generated with respect to Q, when I actually average with respect to P, is going to be the sum of Px minus log Qx. This is sometimes called cross entropy, but it's a bit confusing. But what is this? So this is just averaging the length of code which is optimal for Q, but actually my source is encoded by P. So this is what it is, yeah. My source comes from P, but the code length this is the LQX, yeah, okay. So my code is not a perfect code. But what is this? This is just the entropy of Q, the entropy of P, plus the KL divergence between P and Q. This is something we saw many times. Just how do you prove it? So you just divide and multiply by P here and separate. Okay? So which means that this is going to be the optimal code if I had perfect code. And the excess, the code length that I really pay for, my excess code length is precisely the KL. Okay, so this is nice because it gives another new interpretation to the KL divergence. So it's essentially how much extra bits I will pay per letter if I don't have a perfect code. Okay? So the KL divergence is measuring my mismatch in terms of, okay, I'm using one code, the source actually not exactly matched my code. You're going to pay this KL divergence. So another way of saying it, if I want a perfect code, I want to minimize the mismatch. Okay, but we already saw that. So, so this is the description length is this. This is how much you will get with a perfect code, and this is how much you have to pay if your code is not perfect. Okay, so this is a mismatch extra code length per letter or per symbol. Now, we saw another thing already. So I'm just trying to round up things and connect a few different facts that I showed you before. Yes.
If we go back to the French and English,
Right.
example, what would be P and what would be Q?
So let's say that you are trying to encode English with a code which is perfect for French. Okay, that's what I mean. Yeah. That's clear. So then, of course, your code will not match the statistic of the language. And your description length, this is coming from English, but this actually was perfect for French. So your description is going to be the optimum you could get for French, or for English in this case, if P is English and Q is French. Okay, so this is the optimum of plus the KL divergence between French and English letters. Okay, which we already know, calculated it.
If P is the probability of English, then it means that I'm trying to. I'm looking at a French text, but
I'm trying to encode English with the code which is perfect for French. So this will give me a code, which is actually uniquely decodable, no problem is there. It's going to be too long. And how much too long? Precisely the KL divergence. Okay? So minimizing the code is essentially minimizing the code length or the mismatch. Now we already know, I showed it to you for Bernoulli trials, that the probability of seeing, let's say, m successes in n trials with a probability theta in Bernoulli. You remember this? So this was essentially n over m, theta to the m, 1 minus theta to the n minus n. So this is simply the Bernoulli trials. So this is the probability of seeing m1s or m heads in n coin flips, where the probability of the coin was theta and minus theta. Okay, and I showed you this is essentially very similar, equivalent asymptotically to 2 or e to the minus n, the KL divergence between the empirical distribution, which was m over n, and n minus m over n, compared to theta and minus theta. So this is a very simple KL divergence. And so this is a binary distribution, empirical distribution. And this was the expected. Now, I said it very quickly in one of the classes, and actually it's an important observation that I want you to take a little more careful look at it. So essentially, this is a very general statement. It's not true only for KL divergences, it's true also for any multinomial distribution. So let's say I have letters. I have not only 2, but d or k possible objects. So xk, x1 to xk, and I do an IID measurement out of this. So then the probability of seeing, let's say, m1 up to mk appearances. So let's say think about letters in text or words in text or whatever it is that the object you're thinking of. So in what we call the multinomial distribution, which I hope you all know, is essentially so the binomial number is moved to the multinomial factor, which is essentially so let's call n just the sum of those mi is the total number of objects. So this is n over mi, m1 to mk. So this multinomial thing is just to make sure that you understand. This is just a n factorial over the product of the mi factorial. Okay. So you see that this is a simple generalization of the multinomial thing, because there the m's were n and m and n minus m. So the sum. So okay. So this and this is multiplied by. So this, if there is an expected probability theta 1 to theta or P1, just to make it P1 to Pk, where I know that this sums to 1, Pi, I go from 1 to k. So this sums to 1, so this sums to general, so this is going to be P1 to M1 up to Pk to Mk. This is the multinomial distribution. It's just a simple generalization of this one, of the binomial. Now for exactly the same proof, this is essentially equal to e to the minus n, the KL divergence between m1 over n up to mk over n and p1 to pk. Okay? So again, it's the KL divergence which controls the probability of seeing a distribution which is not the expected distribution. This, in general, this type of result are simple cases of what we call large deviation. Large deviations, theorems. But actually, there's a whole branch of statistics, or branch of information theory, or branch of mathematics, whatever you want to think about it, which is dealing with such bounds. So essentially, this is telling me the probability of seeing something which is not typical, which is not very close to the expected distribution, is decaying exponentially with the KL deviation between them. So this is something I said some of you in some of the breaks. Let's say if I see a coin flip, and I'm giving you 10 runs of throws of a coin, and I see 6-4. So as I config, I see 6-4. Okay. How likely this coin to be uneven? Okay, so this theorem is telling you that this the probability of seeing 6-4 is going like 2 to the minus 10, this DKL between 0.6, 0.4, and half-half. Okay. So this is a positive number, but if n is only 10, so you can estimate this probability. Now let's say that I'm now telling you, look, I throw it actually 100 times and I got 60-40. So it's the same DKL. 60-40 and out of 100, same empirical distribution. But this 100, this 10 is now going to move to, so 60-40 is just like adding another 0 here. So the probability of seeing 60-40 in 100 times is a lot smaller than the probability of seeing 6-4 in 10. So if you see 60-40, you're almost certain that this coin is not even. Very unlikely to happen. If you see 600 and 400 out of 1,000, then you know somebody is cheating you. So this is really, again, this is just another way of saying that the measure concentrates around the typical. So the probability of seeing a non-typical sequence, in this case having slight deviation from the typical one, is decaying exponentially fast. This is just another realization of the same thing. But you see, what is interesting is that, again, it's the code length, it's the mismatch code length which controls this probability, the KL. Okay. So now we can actually apply it in a much more powerful way. So I'm going again to this MDL principle. By the way, it's usually associated with the name of Norman Rissanen. But it's not only him. You can actually derive the same principle from Bayesian view. It's exactly the same thing. So essentially, when I talk about data, I'm giving you data, a text, I don't have a model. And I want to transmit it to you. I want to send you the data. Okay, this is the practical engineering way of thinking about it. I have a text, I want to send you the data. But I'm paying for every bit that I send through the so I want to send you the data in the shortest possible description. But you don't know, so I'm going to compress the data, okay, it's clear. But I need to tell you how I compress the data. So I need to send you the code first. Because only then you can actually decipher it, okay? So I'm going to find some code, which means finding, let's say, some tree like this for my data. And then, so what is really the description length of the data? So the description length of the data is going to be made out of two things. First, build the code. I build the code here. And then encode your data. Okay? I want to send you a big book, but I don't want to pay too many bits, or a movie, or something which is much more popular today. So I'm going to send you, I want to send this a short file, the shortest possible file, which is, again, the shortest possible description. But before I do this, I need to send you the code. Okay, so what is going to be the length of the code? I need to send you a prefix or something, a header which tells me, this is the code I'm using. And then here's the data. So my file is going to be made of two parts. First is how I encode my data, and then I'm sending you the data, and then you can decipher it. Okay? So there are two things. First of all, once I have the code, I'm going to use something which is very close to optimal code. So the code length of the data is going to be log p of x. Say log 2. So this is the code length. Oh, sorry. Code length of the data. So data is some sort of n symbols, and then, but I need also to send you the code. So what is the description of the code? So there should be something here which I call, let's call it L of the code. The length, because I need to send you this header of my file. When you get it, you know how to decode my sequence. If you don't have the code, you don't know what to do with it. It looks like a random sequence. Okay? I think I'm quite consistent with it. So there's the code word. I mean, the code, which is the instance, the way, the length of the description, the code length, which is this. And then there is the code, which is the object with which I generated this description. Okay, it's like sending you the tree.
So the first one is the data, right? It's the way I compress my data.
Right. So the first one is after I have the code, this is the length. This is what I showed you before. But I need somehow to tell you the description length of the code itself. Okay, so this is tricky. What is it? So if you think about it a little bit, I mean, it's not something I can do very quickly, and I don't have too much time. I need to send you this tree, essentially, or something similar to a tree. I mean, to tell you, okay, here is the tree that I was using to encode my data. So how many bits you need, how many symbols you need in order to describe the tree? Yeah, well, I want to give you, let's say that we agree that this is a tree, and we agree this is a prefix tree. I mean, since we can agree this is all a header that don't scale with the data. But essentially, okay, so this was exactly, this is really the idea of the minimum description length. What is the shortest possible description of the code itself? This looks like a second order logic. I mean, there is a description of the data using a code, but I also need to send you the code itself. And I want a short description of the code. Okay, so I don't want to solve it completely now. But let's say, because it's actually a very tricky question, it's actually this question is related to something which we call, in computer science at least, the Kolmogorov complexity of the data. I mean, so you can think about it. What is the shortest program that will generate my data? Okay, that's a very interesting thing. And that's actually a very simple idea that was generated by Kolmogorov first, but actually it turns out to be a very deep idea. So for example, there are numbers out there that have very short description. For example, 2, okay? 2 bits. But actually, even numbers which are irrational that have short description. What I mean, a short description, think about a program that generates this. So, for example, the number pi, 3.141592 and so on. As you know, this is an infinite sequence. But I can actually write a very simple code a one-line MATLAB code that we generated from basic algebra. I mean, not just, of course, the constant pi is structured in MATLAB anyway, but let's say that I want to generate it from scratch. So, for example, pi is, or pi over 4 is the arctangents of 1. Okay, and I can generate the arctangents by a very simple Taylor series. I can write a very simple code that generates the Taylor series of arctangents. And this will be essentially a 2 or 3 or 4 line MATLAB code. So there's a very short code that generates pi. Now let's say that I want a short code that generates other numbers. So it turns out this is just an anecdotal mathematics, which is quite interesting. Some numbers have very short description, like pi and e. And actually all those transcendental numbers have very short description. But actually some of the numbers that have the longest description, most of the numbers don't have short description. I mean, if you could somehow pick an arbitrary real number, which is not that easy to do, because you need some sort of prior distribution over the numbers, and that's not easy to generate, an arbitrary number will have a very long description. This is somehow counterintuitive. So actually, the numbers actually have short descriptions, short codes, short program lengths are very rare. Most of the numbers don't have short description. Actually, of course, we use all those numbers that have short description all the time, like all the rational numbers, all the what we call algebraic numbers. I mean, numbers that are roots of polynomials over the integers and so on and so forth. All the transcendental numbers, but most of the numbers don't have short description.
Is it a matter of convention or
No, it's a proof. Actually, it goes even deeper. Most of the problems that you have that have short description, right, the question has short description. For example, find all the prime numbers. Or give me a list of all the prime numbers which are sums of two cubes of prime numbers. So this question in particular is already we don't have a good algorithm for this. Well, in some sense, so there are problems where I have short description of the problem, but I don't have short description of the answer. Or at least I don't know of a short description of the answer. And there are problems where I can actually easily verify and very hard to test. You know how these problems are called? To find the solution in computer science. If I give you a solution, you can easily check it, but you can prove, or at least under some assumptions, that it's hard to find the solution. These problems are called exactly the NP problems, the NP hard problems. These are the problems where I easily can check it, but it's very hard. I don't have a simple algorithm, or I don't have a simple algorithm means I don't have a short description. But you see, there's already two things here. I mean, short description means a short code length or a short running time. It's not the same thing. I mean, you can have a short code length and a very hard. Okay, so all these very intriguing questions are directly related to what we call Kolmogorov complexity. It's essentially a very naive-looking complexity. Kolmogorov, yeah, you should know this name. Actually, Kolmogorov was this Russian mathematician. Actually, there are many spellings. Sometimes it's written with double F and so on. It's actually a Russian name. So, what was his first name? Andrei, something like this. A. Kolmogorov. And he was really one of the greatest mathematicians of the 20th century. And among other things, he achieved this concept of the shortest possible description or code length of an object. Now, the funny thing about it is that we know that this particular thing is not describable. It's not computable. Okay, so I don't know how much all of you know about the notion of computability or non-computability, but there are some questions in mathematics where we know that there is no way to answer them decisively. So there are things which are undecidable. It's already a weird concept. This comes from Gödel and things like this. I mean, there are questions in mathematics which I can easily formulate, but there's no definite answer within the axioms that we know now. And what Gödel actually proved to us is that anything which is non-trivial, which means contains at least the integers or the arithmetics of the integers, any theory of mathematics or any set of axioms always have undecidable problems. Okay, that's a big headache, but it's directly related to this notion of uncomputable. So there are things which I know I can prove that there is no short code to answer them. So one of those things is, for example, the halting problem in computer science. Yes. Can I give you a code and you can prove to me that this program is going to terminate? Okay, so this is again an undecidable question. Yeah. No, so I'm just playing a little bit, taking a little bit of your break with this notion of short description. And I just want to tell you that short description is a very tricky thing. So I cannot really tell you what is the shortest description of my model. Because if I could tell you this in general, I could calculate the Kolmogorov complexity, and I know that the Kolmogorov complexity, or I didn't prove it to you, but it's essentially an uncomputable number, which means that if I could compute it, I could solve the halting problem. But I can't. Okay, so this is all belongs to the realm of questions which I didn't touch in this course so far, but I think they are actually very, very important and very important for brain scientists. And I doubt if you're going to hear it from anybody else here. Because many of the questions that we ask about the brain can be reduced by some mathematical transformation to questions of this nature. And this is actually quite tricky. So for example, a very naive question like, do I have free will? Or do animals have free will? Do you have free will? Does this monkey has free will? Or whatever. I mean, these are all, in some sense, undecidable questions. I mean, actually, they can be reduced to this type of circular arguments or self-reference problems, which are essentially undecidable. And so, very quickly, I mean, I started with a very technical thing, what is the shortest description of data, and I immediately climb on very high philosophical trees. I mean, what is the shortest program that generates some data, and so on. So, in general, I don't know what this access length is going to be. And so I need to constrain myself, to restrict myself to some specific, what we call parametric models. So if my model has some parameters, I mean, this is actually some version of, kind of related to things like the no free lunch theorems and other things like this in machine learning. Essentially, I cannot learn without some assumptions on my data. So there's no way I can make a universal, really truly universal compression, for example. Something which will take any data and will find its shortest description. There's no algorithm like this, because this would violate this notion of non-computability of the Kolmogorov complexity. But if you want to read about Kolmogorov complexity, there's a very nice chapter in Kova's book on Kolmogorov complexity, and you can read more about it. So what I'm saying that in order to use this description length principle, this is a very, very non-trivial issue. I actually need to specify a parametric family. And when I specify a parametric family, which, let's say, okay, I model my data with Gaussians. Or I model my data with Bayesian models of some degree, or with HMN, or whatever. Once you specify the model, then this is very simple. This is essentially the number of parameters in your data over 2 times the length of the data. That's it. So in a parametric model, this code length is essentially logarithmic in the size of the data, multiplied by the dimension of my model. So usually this type of description, the log likelihood given the parameters, plus the encoding of the parameters, is what we call the minimum description. Okay, let me stop here, because I'm already 5 minutes into the break. I want to take the second hour to talk about. So this was just opening the window for a very, very intricate and interesting question in computation in general. So it looks a very naive notion, this description length, but actually it's a very deep question. It's related to the hardness of computational problems, the hardness, what makes a problem hard and a problem easy, and what makes so some of those problems go very quickly into things which we know are the boundaries of our knowledge. So just to make things simpler again, usually we assume some sort of parametric model here. And if we assume a parametric model, then essentially I need log n bits for every log of square root of n bits, that's what's written here, for every parameter of my model. And that's usually known as Rissanen's minimum description estimation. Now, I'm going to tell you later on that this is a special case of what we call regularization of a model. I mean, it's a special case of simplifying the model by some sort of an assumption, which we always have to do. I mean, we cannot live without it. Okay, let's stop here. Since I have to change the battery anyway. So let's take 10 minutes and then come back. I'm going to talk next about channels communication model. אנדרי קולמוגוב, כן.
הוא בעצם אומר שיש דברים, כאילו הוא מוכיח איזה משפחה של דברים שאי אפשר לחשב?
לא, זה יותר מורכב. הוא אמר, בוא נגדיר משהו יפה. אורך התוכנית הקצרה ביותר שמייצרת נתונים שלי.
אוקיי, אבל הוא...
נגדיר את זה בתור הקידוד האופטימלי שלך. אמרתי לכם שזה מאוד מחשב וגם כקוד. נניח שאני רוצה לייצר את פאי, אז אני צריך קוד של 3 שורות. אני צריך לייצר את הדאטה האמפירי של אח, מדדת אתמול בקופי, לא יודע, עוד מה שאת עושה, או את הטקסט שבוקר את זה, אז אני צריך קוד יותר ארוך, אני לא יודע. עכשיו, אז הייתי רוצה שיהיה לי משהו כמו Universal Equation. אז קודם כל יש לנו, יש דברים שנקראים אלגוריתמי דחיסה אוניברסליים, כמו למשל MTV וכאלה דברים, אז הספקתי לדבר על זה. אבל הם גם כאלה לא אוניברסליים באמת. כי השאלה היא מהו התיאור הקצר ביותר של איזה שהם נתונים, היא Untitled Chapter. כלומר, בעצם זה שקול לגמרי לאורך התוכנית הקצרה ביותר שמייצרת נתונים שלה. עכשיו, שזה מה שקולמוגוב הגדיר אותו הקומפלקסיטי או המורכבות של הנתונים. מה התיאור הקצר ביותר שלה? אוקיי? עכשיו, אם הנתונים שלי נראים כמו מספרים אקראיים, מה שנראה כמו ספרת ביטים, אז אני לא יכול לתפוס אותה. נכון? אין כאן שום redundancy, אין כאן שום structure שאני יכול לתת. אז אורך התיאור שלהם זה הסדרה עצמה. אורך הסדרה, פחות או יותר. אם הסדרה יש לה מבנה, אז כמו שראיתי, הקוד טוב יתפוס את המבנה. אוקיי? אז לא אמר, כן, מי אמר שאני חושב שיש דווקא בשביל תזכור וכאלה דברים, בואו נשתמש בתוכנית מחשב. אז הוא הגדיר את זה קצת אחרת, הוא אמר, אורך תוכנית המחשב הקצרה ביותר, היא המורכבות. עכשיו כאן את יכולה לשאול כל מיני שאלות טכניות, מה אם אני אכתוב בשפה אחת במקום בשפה אחרת? יש שפות שהקוד יהיה קצר, יש שפות שהקוד יהיה ארוך, אז אפשר להראות שזה לא תלוי בשפה. כלומר, עד כדי קבועים, או כל התוכניות הקצרות הן קצרות אותן. אני יכול להעביר תוכנית קצרה בשפה אחת, תוכנית קצרה בשפה אחרת, עד כדי קבועים שלא תלויים בשום דבר מעניין. אז זה לא משנה. תלוי את זה במטלאב או באלגול או באסמבלר, זה אותו דבר. עכשיו, כן.
אז הוא אומר, הוא לא שאל את השאלה, יש את הדרך קצרה לתאר קוד,
לתאר דאטה.
לתאר דאטה, ומה הניסה שלו?
ואז תוכיחו, זה לא עשה קולמוגוב בעצמו, אבל אפשר להראות, אני חושב אולי קולמוגוב עשה בעצמו, שהמושג הזה לא ניתן לחישוב. כלומר, מאוד כללי. כלומר, אין אלגוריתם שתכניס לו דאטה, הוא יגיד לך, הנה התיאור הקצר ביותר שלו. אין. כי אם היה לי כזה, הייתי יכול לפתור את בעיית הספירל. לא ניתן לחישוב.
אבל אם אתה מניח משפחות פרמטריות, הוא לא כן.
כן, אבל משפחות פרמטריות הוא סיפור מאוד פשוט. הוא אומר, תראה לי בעצם את הפרמטרים. בואו נסכים על המשפחה הפרמטרית. והסכים שאנחנו מתארים את זה, אני אחרי תערובת של גאוסיאן. ואז אני צריך להגיד לך את הפרמטרים של המודל. הגאוסיאנים יש להם ממוצעים כאלה, ושוניות כאלה וכן הלאה. זה אומר, לכל פרמטר אני צריך לתת לוג שורש n ביטים. למה? כי בדיוק שאני יכול להריץ את הפרמטר, בעצם מה שאני עושה זה משערך את הפרמטרים על המודל, על הדאטה. ואז שולח לך את האסטימטר של הפרמטרים, אני אומר, במודל הזה קידלתי את נתונים. בעצם אני עושה שני דברים. דבר ראשון, אני ממדל את הדאטה אצלי. מחשב, עושה מודל טוב כמה שאני יכול. נותן לך את הלוג לייקליות ביטים של הדאטה ונתן המודל שלי. ומעביר לך את הפרמטר של המודל, ובשביל זה אני צריך רק לוג n ביטים. אוקיי, עד כדי... וזה נכון לכל מודל פרמטרים עם מספר פרמטרים סופיים. זה משפחה מאוד מאוד מצומצמת. זה הרבה פחות מספר פרמטרים די תטא.
ומאיפה הגיע מודל של...
זה כאן מאוד ארוך. זאת אומרת, אני לא אספק לזה, אבל בעיקרון זה מאוד פשוט. אני נקרא מרב.
מה זה הדי?
די זה ממד הבעיה, ממד הפרמטרים. בעצם קרא מרב אומר לנו שמתוך דאטה סופי, אני יכול לשרת פרמטר בדיוק שהולך כמו 1 חלקי, שהפרמטר הולך כמו 1 חלקי n. זה אומר שהדיוק, מספר הביטים, זה לוג של standard deviation, זה לוג של שורש n. אני צריך לוג שורש n ביטים לכל פרמטר, זה מה שהדבר הזה אומר.
כדי כאילו להבין את זה יותר טוב, אם נגיד אני רוצה כאילו להביא אות, הדבר הזה יהיה האות של ה-S שמגיע ל-S,
האורך הממוצע של ה-S?
כאילו, אם יהיה Q אז יהיה איזה 4,
זה יהיה בעצם האורך הממוצע של ה-S, וזה יהיה הפרמטר של ה-S.
לא הממוצע, זה עבור הסקר הספציפי, זה עבור האות הספציפי.
עבור הקידוד הספציפי,
זה עבור האות הספציפי.
אני עושה שני שלבים, בשלב הראשון אתה מחליט למדל את זה על איזשהו מודל.
נכון.
ואז אתה מקדד את הדאטה שלך הכי טוב עם המודל הזה, ואתה מעביר לי את המודל גם פה.
אז זה הממוצע של...
זה יהיה הממוצע של
הכלום. זה בעצם, זאת אומרת, אם כל זה טוב, אז זה האנטרופיה אפילו.
כן, נכון.
אוקיי, אז אם אני...
נכון, האנטרופיה פלוס אורך הטיעור
אם אני מעביר...
אז האנטרופיה מותנית בפרמטרים של הדאטה.
אוקיי, אז הפרמטרים של הדאטה זה משהו שאני קצת לא מבין, כי אם נדבר נגיד על זה שאני מעביר אות, אז מה כאן הפרמטר, כאילו זה...
אז מה זאת אומרת מעביר אות?
אני רוצה...
אז אם אתה סתם דוגם ודוחץ דגימה, בסדר, אז זה מודל מאוד פשוט.
כן. אבל אני רוצה לדעת כאילו...
אם אני בונה לוקח אות כמו דיבור נגיד, יש לי סטרקצ'ר מאוד מסובך.
כן, אז
מה אני עושה? אז אני בונה, אין לי דוחץ המלוצה של דיבור. אבל יש לי מודלים די טובים שמבוססים על הבנה של סיגנל הזה. שדוחסים אותו.
אז בוא נדבר על משהו יותר פשוט, על מילים. אני רוצה כאילו להעביר מילה אחת.
כן. הדברים האלה כולם הסיסטוסים. הדבר הזה הוא מתחיל להיות נכון שאין גדול.
שאין גדול, אוקיי. כאילו אני לא מבין, כאילו זה בעצם המידה של ה-S, זאת אומרת אם אני אצליח כאילו להביא לו את הגיאומטריה של ה-S, אז אין בעיה של ה-S.
בעצם אתה רוצה את כל העלים.
כן.
עכשיו, מה שאתה מבין זה מספר העלים הוא פחות או יותר אקספוננציאלי בעומק ה-S. נכון?
כן.
אז אתה צריך רק לוגן, אז מספר העלים, אורך ה-S הולך בערך כמו לוגן. ואני צריך, וה-D הזה הוא פחות או יותר כמה ברנצ'ים יש לי.
אז בכלל לא ברור שזה יותר קטן מהביטים בלי קומפרסיה. כאילו מקרים...
במקרה קצרים זה לא ברור.
אז לכן, אוקיי, זה...
במקרה, אם יש לך דאטה בלי סטרקצ'ר,
כן, אז הדבר הזה הוא...
אני לא צריך מודל בשבילו. אבל אם אני יכול למדל, אם יש מבנה בנתונים, אני צריך להעביר לך את האור של הקוד, פלוס האור תיאור של המראה. זה כל הרעיון. עכשיו, אוקיי. כמו שאמרתי, זה נראה מאוד נאיבי, כן? יש כל מיני דברים שקוראים להם קידוד אוניברסלי. זה לא מכיר, זה למפל זי, מה זה למפל זי? למפל זי אומר, אני לא צריך לדעת ההתפלגות P של ליצור קידוד סביר. ומה בעצם למפל זי עושה? אתה מכיר את האלגוריתם? יש שנים שאני נסביר את הערד, יש שנים שלא, שנה אני לא אצליח את הערד. זה לקחת, כל פעם שאני רואה פאטרן שכבר ראיתי, אני כל לשדר אותו, אני מעביר רק את האינדקס למקום הקודם שראיתי אותו. עכשיו אתה בעצם מסתכל על פאטרן יותר ארוכים. אז אתה בעצם מחפש עד המקום הראשון שהוא חדש, שם פסיק, ואומר, אוקיי, זו מילה חדשה, היא כבר חזרה, המילה הזו כבר חזרה, נסביר אותה אחורה. והקוד הזה אפשר להוכיח שהסימפטוטית להיכנס לאנטרופיה.
אז כל המילה הזאת עוברת, כאילו, יש איזשהו פוינטר למקום אחר, שאת המידע כבר...
בדיוק, זה כבר העברתי.
אז המילה הראשונה שראיתי, אז הטקסט הרבה בדיוק יותר, אותה מילה השנייה שאני רואה כבר...
אז אם המידע שלי הוא באיזשהו מובן חוזר על עצמי, כמו טקסט, אז אני יותר ויותר פעמים אראה דברים שלא ראיתי, פחות פעמים אראה דברים שלא ראיתי. לכן אני אוכל להעביר פוינטרים. והפוינטרים האלה הם הרבה יותר קצרים מהדאטה עצמו. וזה הרעיון של למפל זי. עכשיו, אתה חושב על זה, למה זה לא סותר מה שאמרת פה באופן קומפלקסיטי?
בדיוק.
משום שיש כאן, מתי זה יעבוד טוב?
כשיש לי...
שהסדרה היא מה שקוראים סטציונרית וארגודית וכל ספינות טיפות כאלה. שבעצם אני יכול לקרב אותה על ידי מודל מרקובי בסדר סופי. עכשיו, זה משפחה מאוד מאוד מצומצמת של ספרות.
כן.
הספרה האנושית בין היתר היא לא כזאת.
כן, זה כאילו, זה מה שאמרנו, כאילו...
אני יכול לקרב אותה, אבל היא לא מודל מרקובי יותר. אבל באופן כללי, עכשיו, אפילו אני אומר דברים פשוטים, כמו לתאר מספרים טבעיים. תאר לי את הסדרה של הביטים בפיתוח האינסופי העשרוני או הבינארי של המספר. תן לי אלגוריתם שיכול לייצר את זה באורך שיותר קצר מהסדרה עצמה. אם אני יכול לתאר את זה לתיאור קצר, עדיין המספר הוא באיזשהו מובן פשוט. אני אומר שרוב המספרים לא ניתן לתיאור קצר. וזה קשור לעובדה שרוב הבעיות אין להם פתרון פשוט.
אבל מי שנגיד יש מספר ועל 20
סופי. כל המספרים הרציונליים.
הרציונליים או הטבעיים?
הטבעיים בטוח, אבל גם הרציונליים יודעים חלק מהרציונליים, ניתנים לתיאור קצר יחסית, אבל גם כן לא קצר מאוד. אתה יכול להראות שאורך התיאור גדל כמו המכנה של השבר המצומצם בריבוע.
אוקיי. כי זהו.
כלומר, אם אני יכול לקרב את המספר של היעדר רציונליים באופן יעיל, אז אני יכול לתאר אותו תיאור קצר, היעדר רציונליים. אבל אם הרציונליים הולכים ונעשים יותר ויותר גדולים מבחינת הגודל של המכנה, אז השברים האלה קשה לי מאוד לנעשה תיאור. במובן הזה, המספר שהכי קשה לתאר אותו, עכשיו יש כאן איזה ניואנס מעניין שהזכרתי אותו במשפט אחד. יכול להיות שהאורך הקוד הוא קצר, אבל בשביל להריץ אותו צריך אינסוף זמן. האם זה אומר שהתיאור שלו מספר הוא פשוט או לא? אז במובנים של חולמוגו, כן, הוא פשוט, יש לו אורך קוד קצר. אבל במובנים הפרקטיים זה צריך אינסוף זמן של להריץ את הקוד ולייצר את המספר, אז זה אומר שהוא לא פשוט. אז אני צריך לקחת חשבון שני הדברים, גם את אורך התיאור וגם את זמן הריצה. וכאן אנחנו רוצים לשאול שאלות של מדעי המחשב של אורך אינטליגנטי. בסדר?
בסדר, תודה.
אוקיי. זה אגב נכון, זה משהו כמו 200 כאילו. Okay, so I know that this is getting into all sorts of topics that I'm not, unfortunately, unable to describe in great detail, but I simply wanted to know about them. So somebody asked me, where is this coming from? And so D, as I said, is the dimension, the number of parameters of my model. And this half comes from square root. It's actually log of square root of n. And just to give you a basic intuition, why is it true? So the Kramer-Rao bound, you remember that if essentially what I do here is I first model my data, let's say with some parametric model. And I have to choose a parametric model. And we have to agree on the parametric model on both sides of the communication. When I send you the data, you know that I'm using, let's say, Gaussian mixture model or something like this with k Gaussians, okay? So and essentially, every one of those parameters, what I do in order to fit the model is essentially doing a parameter estimation on my data. Now, then I want to send you the parameters of my model in the shortest possible way. But so what is the precision that I need for each parameter? It's essentially 1 over the standard deviation of my estimator. I don't need more bits than this because and you know that the standard deviation is going to be bounded by the square root of the minimal variance, which goes like the Fisher information over n.
Why do you need the standard deviation? I mean, how do you actually do it?
Okay, so the intuition again is very simple. Imagine that my parameters are bounded, like parameters of a Bernoulli distribution. So essentially, so let's say they're between some number. They always can think as numbers between 0 and 1. Okay, that's really matter. So if they're not bounded, I compress them to 0 and 1 in some sense. I map them into 0 and 1 in a one-to-one way. Okay, and then I'm telling you, okay, so essentially I'm going to bin the interval 0 and 1 into bins. I don't need to give you the exact real number. It's enough to give it to you within the precision that I can actually trust. Okay, but I actually showed you already. I mean, we know that the variance of an estimator is the minimal is actually 1 over n times the Fisher information. Okay, this is the Kramer-Rao bound, which means that the standard deviation goes like 1 over square root of n, proportional to 1 over square root of n. And in order to send you the parameter, I don't need to specify it more than essentially the standard deviation of the estimation. Because if I give you more bits than this, you don't know it. I mean, it's within the noise. So I need to divide the interval into bins or shorter intervals, where the size of each interval is essentially proportional to 1 over the square root of n. Okay, so I have square root of n number of options here. Now, in order to, and going to be equally likely if I did it correctly. So essentially, in order to encode my variable in the best possible way, I need a map of the parameters into the unit interval, which is uniform. Which means that essentially the code length of this bin is just the log of 1 over the square root of n, or square root of n. So log of the square root of n here is essentially the number of bits that I need in order to encode a good estimate of my parameter. Now, I have to do it for every parameter, so I multiply by the dimension of the parameter. Yeah? Sure.
How is sending the parameter give you the real code?
No, okay, so now we agree, let's say that we are going to communicate, as I'm going to describe in a second. I mean, it's all communication. I want to send you the data. So first of all, let's say that we agree in advance that we are using Gaussian mixtures. If not, okay, I'm sending you, this is my model as another header, but this is constant.
What do you mean by we're using Gaussian mixture?
So I'm telling you, I want to send you an image, okay? So what do we do today? I'm telling you this image is going to be encoded by JPEG. What do I mean by that? The JPEG is a well-known code. I mean, so you download the JPEG decoder, even if you don't do it explicitly. And then we both agree on the way I encode my data, and then you have the way of decoding it. That's the way you send data today, okay? We agree on the code, JPEG, whatever. If I'm actually using a different code, then you have a problem. You need another decoder. So you have to download a different decoder from somewhere in order to open your file, okay? That's what we do all the time. But now I'm telling you, okay, you agreed on JPEG, but this JPEG actually has parameters, which means I need, either I send you the full description of your data, of your model in some sense, but I need to send you the model with the parameters that you actually estimated from your data. So what you do is the following thing. First, I choose a parametric model. Then, let's say like Gaussian mixtures, or whatever, HMS, or JPEG, or whatever. These are all statistical models. And then I use this model in order to encode my data. How do I do this? I optimize over the parameters of the model to get the shortest possible description, which was completely equivalent to minimize the log likelihood of the data given the parameters. Okay? So I estimated the parameters for my model, for my data. And then I have a probability for every instance in the data. So I build a code based on the parameters, which allow me to send it in log p bits.
So each picture has been compressed with a different set of parameters.
Yeah, but now I need to send you the parameters because these are known to me, because they're based on the data. So in order to send the parameters, I need log square root of n bits for every parameter. This is the description of the parameters. So the description length here looks essentially like d over 2 log n. The d is the dimensionality. Okay, so that's the whole idea. But remember, why log n? Because I'm using the Cramer-Rao. I know that the variance goes like 1 over n, or the standard deviation goes like 1 over square root of n. And so I divide my interval into square root of n bins. And then I need log square root of n bits in order to specify in which interval my parameter lies. Okay? Because this is just a uniform variable with square root of n options. Okay? So that's it. That's the proof. Yes?
So can you give an example of a parameter in the case of an image or in the case of an
Yeah, so in the case of an image, let's say I want to send this image. So what I do is some sort of, there are all sorts of parameters here. For example, which colors appear there. So I'm modeling it by some sort of a model which essentially assigns probability to a pixel given its neighborhood or something like this. And this model has parameters. I mean, it may depend strongly on, so for example, the size of the neighborhood. What is the I want a good description of this picture. So this picture has some structure in it. So I want to capture this structure, and how to do it is a full art of how to compress images. But essentially, I compress the image, and but this compression is based on all sorts of measurements that I did on this image. For example, it has very strange colors. I mean, purples and green and all, which are not very common maybe in other pictures. So I don't want to use some sort of universal compression of colors because this has very specific colors. If I use a universal palette of colors, I may waste bits because this doesn't have red or doesn't have I don't know, white. So I have there are colors that I don't want to tell you about. So I'm distorting my distribution of colors to this image, which means that I'm actually modifying my model from some sort of universal compression of colors to this specific color. Then I get better description. So I need to tell you how I modify the parameters. And that's why I need to send you parameters. Yes, I know that I'm really out of time, but okay, go ahead.
But is this code unique?
No, the code is never unique, but the length is unique. Codes, there are many, many optimal codes, or very close to optimal codes.
So
that's why I need to specify.
But when you build the optimal code based on the parameters...
Yes, so I'm choosing a parametric family. I'm encoding my model in this parametric family, find the best parameters for this data, and then I'm sending you the parameters and the description of the data given the parameters.
But how would I know which code you mean if it's not unique?
That's why I send you the parameters. We agree on the parametric family.
So it's unique within the parameters?
Yeah, within the parametric family, you know how to. I'm sending you enough to reconstruct a unique code on your end. Okay, now, okay, I know that this is just opened a Pandora box of questions, but I want to go on. And I'm very happy that you find this interesting because it's an interesting question. What is really the short description? But it's actually a very fundamental question. You see, this is at the core of modeling data and actually at the core of learning in general. Okay, so I'm going to extend this, but actually switch to an entirely different topic, which is Shannon's communication model. Okay, so this is again, there's a nice story here. So we talked about data compression. And I already had in mind essentially this picture that I have the data and I want to send it to you. and and I want to send it in the most efficient way, so I want to compress it first. And just by thinking about this question, we already came up with some very fundamental concepts like the description length, the complexity of the data, and so on and so forth. Now, in general, when you talk about communication, what we call two-side communication or point-to-point communication, we have what we call a source. Okay, a source is a source of information. Okay, so it's somebody who is generating data. Now, so essentially generating symbols or words or whatever you want to call them. Okay, in some, so there are let's call them words but in a very general sense, or symbols, which are essentially those X's, which have some probability distribution. You know what? Because I need X for something else, let's call this W now. So this word, this source is generating. It has some probability distribution. It's already a very strong assumption. But I assume that there is some structure there that this source is generating, and it's a fixed probability distribution. So for example, think about language. I mean, this is the canonical example, which is as complicated as you want, so it's good enough. I'm generating images, I'm generating spike trains, I'm generating whatever you want. Okay, so this word, this object, which I want to send through the channel, there is another end of it, which is what we call the receiver. So there's a source and receiver. Okay? And so what is and this is what we call point-to-point communication. I mean, I'm sending you. And there are, of course, different models of communication. I can send to many people. I can broadcast. I can send to a group of people. A group of people can send to a group of people. There's, the internet today is giving us many, many different types of communication, but this is the simplest possible one. Point-to-point. There's one source and one receiver. And what's the problem? So the problem is, why is it not just, okay, compress? Let's say that there is a cost in the communication. So essentially, the point is that there is something here in between, which we usually call channel. And this channel can be anything. I mean, it's a very abstract notion. So think about, for example, now I am sending you information, hopefully. So there is some source of knowledge or whatever in my head, a source of information. And I'm actually transmitting it to you right now. How do I do it? I mean, I first of all encode these messages in sound. Okay, in vibrations of air. Essentially, this comes out of my mouth through a very complicated mechanism, the vocal tract and all that, the vocal cords, and there's a mechanism there, which is some sort of an encoder. Okay, and now this sound is moving through the air between us. So essentially, it's vibrating the air in this room all over the place, and eventually hit the eardrum in every one of you, I hope, and vibrates it. Now, then this, as you may know, I mean, this eardrum, these vibrations of the oscillations of the eardrum is encoded in very different ways. I mean, first of all, it's pushing all these bones, and then the inner ear and the cochlea is doing some sort of decomposition into frequencies, and then it's encoded in spike trains in the auditory nerve, and so on and so forth. And eventually, after a very complicated cascade of encoding and decoding of representation, it comes to somewhere in your cortex, A1, A2, A3, whatever, you don't really know. And somewhere there, eventually, you get a message, which is the content of what I had in mind telling you. So this is a very complicated cascade of transformations. And every one of them, the physical representation of the object of the information is very different. I mean, actually, it started with my brain somewhere, and then it was encoded in muscle movements of my vocal tract and my tongue and lips or whatever, which is very complicated code by itself. And then this is encoded by sound wave, which is encoded by vibrations of your eardrum, which is encoded by spike trains in your auditory nerve, and so on and so forth. So this channel, this is actually a physical channel, which can be many, many things. And in general, it's many, many things. And eventually, you are, on the other end, trying to recover my messages, with some accuracy, I hope. Of course, you don't. So in general, there's some noise in this channel. So something comes into this channel. Let's call this X, just for simplicity. And something else gets out of the channel. Let's call it Y. Now, X and Y may or may not be of the same nature. For example, the sound wave that gets out of my mouth is moving through the air between us. There could be all sorts of noise here, which may affect the way you receive it. But then it's encoded by vibrations of the eardrum, which is a different type of wavelet, which is immediately encoded by vibrations of the basilar membrane in the cochlea, and so on and so forth. So many, many physical transformations of this information. And eventually, as I said, after several stations of spike trains, and it goes to the cochlear nucleus, and it'll go to the inferior olive, and go to the thalamus, and goes to the long station, which you may have heard of, a transformation. Eventually, it is represented somehow in a way which you don't understand in the cortex, in similar way to the way I think it is represented in my head in the cortex, and both of them are unknown to us, and we don't really understand how it is represented, but obviously there's some sort of representation there. So I want now to capture the essence of it in some sense. And what I'm saying, there is some sort of channel between my initial representation and your final representation of the information. Yes?
So the channel can perform transformations that are not necessarily noisy on the...
What do I mean? No, so any transformation which is not...
In the auditory system, you...
Yeah, okay. That's of course a very important question, a very good question, and very much in the heart of what I'm trying to understand all my life. How is this transformation improving or disproving? But there is noise. Okay, so in general, that's essentially the model of Shannon. This is a complicated thing. We just assume that there's some probability distribution, some condition probability distribution. So again, this is a very complicated thing just about the hearing, and the same is true for the visual system and so on. There is an infinitely complex cascade of transformation representations in this.
All the noise and everything comes in T?
Yeah, but in my language, there's a distribution. I put X into the channel, I got Y out of the channel, and the only thing I really care about is this channel distribution. How the output depends on the input. Okay? So that's, this is already a huge simplification of the problem. But without this simplification, we cannot do anything. It turns out to be a very powerful simplification. So there is a source, okay, and this source was characterized by some probability over what I call words, the objects that I'm trying to send you. Okay, I'm actually not trying to send you words. I'm trying to send you ideas, which are encoded by sentences, which are encoded by words, which are encoded by phonemes, or are encoded by sound bits, and whatever you want. I mean, there are many. Even in this, there's already a long list of encoding, decoding processes. But let's simplify things. Okay, so there are words here. So these words are coming out of my mouth or whatever, out of my source. But the channel has entirely different nature. So we think about the channel as some sort of alphabet. It has, let's say, bits. Without loss of generality, as we already discussed them. So although actually the sound waves within us are not bits, but we already know how to represent sound by bits. Okay, we just sample it and turn it into bits. So there is some sort of, I can always think about this channel as a discrete channel. This actually is not obvious at all. This observation of Shannon that all the channels, all the physical channels should be actually discretized into discrete symbols was a very big stumbling block in understanding the theory. But this was really the beginning of what we now call the digital age. The fact that I can take any analog signal like sound wave or electric voltage or whatever, or electric current, all those physical things, I can think about them as actually discretized in finite alphabets. This is a very, very important step. I didn't talk here about continuous sources. I know that Ravit talked a little bit about differential entropy, things like this. We simply don't have time for that. But there is a way of taking everything, every continuous analog signal, and turn it into discrete symbols. And this is sufficient. This is unique. I don't lose anything by doing this.
So X is a discretization?
So X is some symbols. Symbols in some alphabet. Something.
They don't come already in bits? I mean, the
No, the words are not necessarily bits. I mean, they can be words. I mean.
and then the channel transforms.
Yeah, so I need something in between. Okay, that's why I leave this space here. So these are symbols. Let's say that for simplicity, the y are also symbols. This y belongs to, let's call this alphabet of x, and this is the alphabet of y. The alphabet of y can be the same as the alphabet of x, and this is bit and this is bit, but not necessarily. I mean, I can think about sound waves that come out of my mouth and the spikes in your auditory nerve. Entirely different things. So, and I can think about the x as my sound wave, as my voice, and as y as the spikes in your auditory nerves, and that's okay. I mean, so there's a big channel somewhere. The question is, what is the connection between y and x? And I argue that everything is captured by this conditional distribution, P of y given x. Okay. But as Mo said very correctly, I mean, I need some translation. I need to take this into this, and then send it. And unfortunately, there is noise in general in this channel. What do I mean by noise in the channel? Noise in the channel means that y is not a one-to-one representative of x. If it was a one-to-one map, then there's no noise. Okay, so just a translation of the symbols. I don't care about this. The problem is that there is noise. That usually I get x and I get similar or the same y for different x's, or I get different y's for the same x. This is the real problem. Okay, so what Shannon really, in a very, very inspiring and very illuminating model, told us, look, there must be something here which we want to call encoder. And then there is another thing here, okay, that's to make it similar. Another thing here, which we want to call decoder. And this decoder is then translated into something the receiver can understand. Not necessarily. I mean, as I said, I mean the receiver and the source and the receiver, by the way, can be different things altogether. But usually we think about them, let's say, as humans or something like this. And eventually, so this, if this was a text in some book, I want here to generate the text in the same book, in the same language. But not sir. Who said maybe I want to translate it to other language in between, or maybe I want to send it in a totally different way. I mean, this was sound. This is text. These are all under this type of model. Yeah, okay. Now, the point is, I mean, the really ingenious part of the work of Shannon is that he managed to characterize everything that really matters in this model in a way which is completely independent of the physics of the actual way that things are encoded in the world. And this was really the greatest revolution. So essentially he said, look, I already told you that the complexity of the source in terms of what is the number of bits that I need actually to send you is completely characterized by one function, which I call the entropy of the source. Entropy of the source, in this case, the h of w. So I know that this, in some sense, is a universal one-number characteristics of the complexity of the source. So if I know this, I essentially know how many symbols, at the minimum, what is the minimum number of symbols that I need to send you. But so there must be something here which they're going to call source coding. So I'm going to break this into two pieces, and then we see that eventually we can't always do this, but this was a very important conceptual step, you know. So the first piece is what he calls source coding. And this source coding is essentially data compression. So let's call it, so this is data compression. Okay, data compression. It's a compression. So let's do the following. First of all, independent of the channel, find a way of minimizing the description of my source. Okay? Sounds very simple. Okay, and then, okay, so I do it on both sides. I break this decoder I know that this is a headache for those who are trying to write down what I'm writing, but it's all right. I break this decoder. This is the advantage of a board. You can wipe it. So I break this decoder into two pieces. The first piece is compression and then decompression. Decompression. This decompression is what we call expanding. I mean, it's not like what we do in your computer, zip and unzip. Okay, you compress your data as much as you can. Then it's okay. It's already stored in the shortest possible way. And then you assume that on the other hand there's this decoder or decompression, and you're both using the same code or the same program, so you know what you're doing. Now, after it is compressed as much as I can, there is this problem of the channel. So the channel is something bad. I mean, it's going to introduce noise. So what do I do there? So I need something which I'm going to call channel coding. Here. Channel coding. And channel decoding. And this is essentially supposed to take care of the noise in the channel. So, in other words, if there are errors in the channel, that y is not exactly a one-to-one function of x, then I need something which we now call error-correcting code. So those two things is what we call error-correcting code. Okay, that's the whole story on its own. But the genius of Shannon, again, I mean, I don't use this word very often, but this is certainly one of the cases where you can use this word, is that he was able to realize, I mean, it didn't take it not in one step, in several steps, that, okay, so there's something that takes the compression into the channel coding, and then there's noise in the channel, and from the channel I decompress. What he realized, and it was a complete surprise to most people at the time, to everybody at the time, that actually you can correct the code perfectly. Essentially, you can take any noisy channel and turn it into a clean channel as long as you bound the rate of transmission somehow. I mean,
the nature of the noise.
As long as you, so whatever the noise is,
You need to know it though.
in a sense, yes, you have to know it. You have to know something else about the noise. If the channel is not completely random, in the sense that y somehow depends on x, even in a very noisy way, you can still correct the errors perfectly. So this was a big revolution, because it tells you essentially I can have perfectly clean communication as long as some condition met. And I want to state those conditions because this is really very important. Okay. So I'm not going to be able to prove much, but maybe, not today. Okay, so I want to give you the intuition. The intuition is extremely important. And then everything follows is simple mathematics. It's not so simple, but it's simple enough.
What do you need? I mean, before the noise, do you have something that deals with the noise before you introduce the noise?
Yeah. So this type of separation of first compression and then error correction it's called in information theory the separation assumption or separation theorem, which means that I can decode, I can cover my channel with some sort of an error correcting code and make it essentially clean, irrespective, independent of what the source is. So I do two steps. First I compress, then I error correct, and then I decompress and get the message. But this is an assumption, a very strong assumption, that I can always do this separation. And actually, in reality, in biology, for example, we are not using this strategy at all. But let's first understand what this strategy is. Okay, yes?
What do you mean by error correcting before the noise happens?
No, I'm error correcting. I'm not sure I understood the question of Moore, and therefore I probably didn't answer it. But I don't do it before. I mean, I do something to the channel coding.
So if you know the noise is...
I don't know the noise.
So the...
Okay, so let me... So first, so we talked already about data compression. So in principle, there is a way of generating a short description of my code, of my source. we spent 2 weeks talking about. Okay. Now I want to talk only about this entropy, the channel coding. Okay. So how do I correct error noise? What is really so usually. Okay, so the theorem that it's called the channel coding theorem. Has this essentially want to be a formal, more or less formal. It's actually it's informal in principle, because I'm not going to get into details. So if you need a number that characterizes how y depends on x. Using information theoretic terms, what would you use? Oh, still not there. So mutual information, for example, if you remember it, is telling me how y depends on x. So Shannon's really remarkable result was let C, it's something which I call the capacity of the channel. It's also C for channel, but be the maximum over all possible p of x's, where x is now the symbol that enter into the channel. It's after the compression. So let this be the maximum of the mutual information between x and y. So given a channel, given p of y and x, I define the capacity as the maximum mutual information between x and y over all the possible p of x. Now notice that if y and x are independent, which means y doesn't know anything, doesn't tell you anything about x, then this is going to be 0.
So C is not a number, it's probability?
No, C is a number. It's a number.
It's maximum over P of x, P of x.
No, I mean, given this,
Okay.
given this I define, and let's see, and this is the capacity of the channel. Of the channel. Okay, so this is the channel capacity. Okay, this is one number. Now this number, it's bits. Okay, because we measure information in bits. It's the entropy of x minus the entropy of x conditional y, or the entropy of y minus the entropy of y conditional x. Now what I'm telling you that if my rate of symbols after the compression is less than the capacity of the channel, then I can recover the signal without errors.
It's what?
Okay, so that's the important part. So I defined, this is another definition, let the rate of the source let's call it rate R, be the 1 over n let's find it in words first. The number of symbols per unit time. So per unit time, you can think about it. If I generate words in some rate, so right now, let's say I generate 2 words per second or something like this, or 3 words per second if I speak very quickly. So there is certain rate of information that I generate. Okay? I'm sending you essentially, so the only new thing here is that I'm thinking about information per unit time. Okay, I'm really almost out of time now. So this is which essentially, you can think about it as bits per second in my code. So let's say I encode this source. Every word is encoded by some tree in some number of bits. But then I need to catch up with, I need to send you those words in the speed that I'm actually speaking, which is, let's say, 2-3 words per second, which means you can translate it to some number of bits per second. Okay, so if I speak very slowly, it's a slow rate. If I speak very fast, it's a fast rate. So the only new thing new element that I'm thinking about is per unit time. You can think about it also as per word on average. Okay, so this is per unit time, and this unit time can be the second, or can be words, or can be letters in my text, or whatever. So there's something intensive. I'm sending information all the time in some rate of information.
What does it mean, number of symbols per word?
So remember, essentially what I do here is use source coding, use data compression, so I have some sort of tree. I take the words, and each one of the leaves of my tree is a code word with some symbols of bits, let's say. Now, now I'm sending you 3 words per second. So the number of bits per second is going to be the average code length per word, multiplied by 3, which is the number of words. So this is going to be the number of symbols that I'm going to send you per second. Okay? So this is very important. Think about rates of information. So far we talked about compression, but now everything happens in time. So I'm thinking about information per time, and I'm almost out of time. I really don't want to go. I just want to formulate the theorem, and I'm going to prove it next Monday, because I really need you to have an exercise. So the theorem is that, so this is rate, the number of symbols, let's call that channel symbols,